I'll begin. Is the audio bouncing? Excellent. Heavenly Father, we thank you for this morning. Again, Lord, I thank you for these students who just prayed with us today. Help us to, again, Lord, glorify you in what we do. We thank you, Lord, that your righteousness that we can have if we just accept you into our heart. And we thank you that you give that gift so freely. Because we know that our righteousness amounts to nothing, and we know that we're nothing. And it's only your grace that we have anything, Lord. And I just pray that you be with us today again. Help us to glorify you in what we do. In your name I pray, Lord Jesus. Amen. Okay, so let me prove some things for you. I owe you proofs. Proofs. All right, so this is Koshi's mean value theorem.
Is this a part of 11.5?
That's a good question. I don't remember. 11.5.2. 11.5.2. Yeah, page 557. But here's the theorem. Suppose f and g are differentiable on the closed interval from a to b, all right? And g prime of x is not equal to 0 for all x in the open interval from a to b. Then, here's the punchline, there exists some r in the open interval from a to b for which what? For which f prime of r over g prime of r is equal to f of b minus f of a over g of b minus g of a. It turns out that this little, it's okay, I got it. It turns out that this little theorem basically gives you the tool you need to prove at least one case of L'Hopital's rule. So the proof is by Rolle's theorem. Do you guys remember what Rolle's theorem says? For example, if I take this marker, right, and I throw it like so, you can study its initial and final y, which are what? The same, right? So y initial equals y final. Rolle's theorem says that there's somewhere in the flight of the marker where the y velocity is 0. In other words, it says if f of b is equal to f of a and f is differentiable between a and b, then there's somewhere where f prime of c is equal to 0. It's a special case of the mean value theorem, which states that the average rate of change is matched by the instantaneous rate of change at least one point in the interior of the interval of consideration. Now, here the proof we can define. What we do is I'll basically follow the book, and he makes up this function, and he doesn't call it h. I'm going to call it h because he calls it big G, but I don't want to be confusing with the little g, so I'm just going to call it big H. And what big H is going to be equal to, it's going to be equal to like f of x minus f of a, all right? And just to keep the writing to a minimum, I'm going to say change in g plus the change in f, all right, times g of x minus g of a. Now here, I'm defining change in f to be a number and change in g to be a number. What are those numbers going to be? The numbers I'm thinking of, change in f is f of b minus f of a, and change in g is g of b minus g of a. So notice that the change in f and the change in g, these are fixed numbers for this discussion. Okay? Now, what we have here, notice h is both continuous and differentiable on the closed interval from A to B. All right. In fact, I only need differentiability on the open interval, but hey, I got it at the endpoints as well, so that's nice. Now, how do I know that? I mean, look at the formula, right? You're taking a number, and you're like subtracting it from a continuous differentiable function, multiplying it by a number, right? I mean, so look at these formulas. We're doing nothing more than like adding numbers or multiplying by numbers functions which are continuous and differentiable. So of course, that still gives you a continuous differentiable function because of our limit laws and derivative rules, right? Notice and also observe what? What's h of a equal to? It's f of a minus f of a, change in g, right? Plus change in f times what? G of a minus g of a, which is otherwise known as 0, right? Yeah. How about h prime of x? What's the derivative? It's what? F prime of x times change in g, right? Plus the change in f times g prime of x. What happened to the g of a? What happened to the f of a in the derivative? They're constants. They differentiate to 0, right? So you notice by what I have up here, I can apply Rolle's theorem, right? Because I have h of a is equal to 0. Oh, one other thing, right? I'm sorry, I forgot to check. What else do we need to check? I should probably put it up here. Likewise, oh, fine, I'll do it down here. H of b is what? I forgot to do it. You have f of b minus f of a, change in g, plus change in f, times g of b minus g of a. But what is that? Well, that's delta f delta g minus delta f delta g, also known as 0. So this function h is 0 at a and at b. It's continuous, it's differentiable, so I can apply Rolle's theorem to h. That means that there exists an R in the open interval from A to B such that what? Such that h prime of R is equal to 0. But what is it to have h prime, if h prime of R is equal to 0, what does that give us? Well, it gives us f of R minus f of a delta g plus delta f times f of, g of r minus g of a. That's all 0, right? But you can solve this, right? You can solve this, and what do you get? Oh, I'm an idiot. Is this what I'm supposed to look at? I'm not supposed to look. If that's the h itself, what am I supposed to look at? Duh. This one, right? Yeah. Sorry. So we plug r into that. So we've got what? We've got f prime of r delta g plus delta f g prime of r is equal to 0. Oh, you guys shouldn't let me get away with that. I can talk you guys I could sell you guys to Brooklyn Bridge. Not that if man, you guys just never stop me about anything. You guys got to be meaner to me. Look, this isn't going to work. That plus this plus, because this plus gives you delta f, delta g, plus delta f, delta g. I'm sure one of you noticed that 3 minutes ago, right?
I was trying to figure it out, to be honest. I was not sure why you were doing
All right. So we go back. This is a minus. This is a minus. This is a minus. This is a minus. This is still a minus. So I made 2 errors, right? The outcome was correct. It's just that is why it's 0. That's important, right? Because that also puts a minus where? Right here, which is very important, because then when we solve, right, for f prime of r over g prime of r, what do we get? Delta f over delta g, right? Which, by the way, is f of b minus f of a over g of b minus g of a. Which is what we're trying to prove, right? That there's this r such that the ratio of the instantaneous rates of change at r matches the just the difference in f and the difference in g over the entire interval.
How should this statement apply Rolle's theorem to? Is that an H?
Yeah, h. Sorry about that, guys. I know it's too early. But now, I did algebra there, right? How do you get from here to here? What 2 things do you need in order to make this step? I'll do the easy one. G prime of r is not equal to 0 since what? G prime of x is not equal to 0 for all x in the open interval, right? That was given. That's part of the assumption. Okay. How do I know that g of b is not equal to g of a? How do I know that g of b minus g of a is? What would happen if g of b, if g of b, right, was equal to g of a, what would that tell you? There exists some c, right? Such that what? You could apply Rolle's theorem to the little g. It would say that there exists what? There exists some c between a and b such that g prime of c is what? But is no allowed, right? Is no allowed. So that is impossible. You cannot have g of b equals to g of a with the other data, which is given. So it's safe to divide by g of a minus g of b minus g of a. And so the theorem stands. All right? How many people here are comfortable with Rolle's theorem? Like 2. How many people have this is vague, fuzzy notion of someone talking about Rolle's theorem several years ago? That's most of us, right? Yeah, understandably. It's something we cover, but you don't tend to use too much. But it is an important, it's really what's behind the mean value theorem. It's ultimately what's behind Taylor's theorem. We will use Rolle's theorem again once we derive Taylor's approximating polynomial theorem. All right. Now, so then that leads us to the L'Hopital's rule, right? If the limit as x approaches, well, let me just say it this way. If f of x and g of x both go to 0 as x approaches c from the right, and a little more fine print here, and and g of x is not equal to 0, and g prime of x is not equal to 0, well, let's say on the interval like c to, say, c plus epsilon for some epsilon. So you need that the function is non-zero and the derivative is non-zero to the right of the limiting value. Right. Then, here's the punchline. F prime of x over g prime of x going to gamma implies that f of x over g of x likewise goes to gamma as x approaches c from the right. That's a special case of L'Hopital's rule. We usually do this the opposite way, right? We start with f of x over g of x, and we trade it, right? We trade it for the ratio of the derivatives. We find out that that makes sense, and then we kind of work backwards, right? So every time you do L'Hopital's rule from this perspective, you're kind of like, all right, I talked to my Calculus 1 students about taking out, it's like taking out a logical loan. A lot of times when you do something like limit of f plus g is equal to the limit of f plus the limit of g, well, when does that make sense? This only makes sense if the subsequent limits exist, right? So if you don't know that, when you make this step, I say you're taking out a logical loan. You're assuming something that you may not yet know. But as you go on, you do some more steps, you find out, in fact, yes, these do exist. So in retrospect, this step was valid. That's how we tend to calculate, right? The same thing is true of L'Hopital's rule from this perspective, right? You apply L'Hopital's rule, and it simplifies down to something you know. Then, in retrospect, the application of L'Hopital's rule was valid. It's a little bit greedier than that, though, because as I mentioned, L'Hopital's rule is still true in the divergent cases. So, if you find that after you apply L'Hopital's rule, the resulting limit diverges, it's probably, I think it is true, but I'm a little, I'm claiming something I haven't seen written in textbooks, but it's true from my experience. If you apply L'Hopital's rule and you get something that diverges to infinity or diverges to minus infinity, then it's the case that the original limit before you applied L'Hopital's rule is likewise divergent to plus or minus infinity, right? So I think this theorem has extension to the case that you replace gamma with plus or minus infinity, But it's still that kind of logic we're using. We're always applying L'Hopital's rule. Eventually we find something that we understand without indeterminacy. And then in retrospect, you're like, oh, okay, well then that L'Hopital's rule was in fact right. Now that's not actually how you think. You just apply L'Hopital's rule and you probably forget about the fact that when you do that, you're assuming that the thing later has to go to somewhere. That's all wrapped up in the fact that we have to keep calculating until we come to something that's not indeterminate, right? Doing that makes the application of L'Hopital's rule in retrospect valid. It would get tiring to say all of this every time we apply L'Hopital's rule, so we don't. That seems somewhat inconsistent with your insistence that I write everything down in the last quiz problem. I know. I can't be mean all the time. What can I tell you? All right. So here's the proof. If we look at, so assume the data up here. Assume you have f of x and g of x going to 0. I also need to, there's something else that I'm assuming. If I'm writing this, what am I also assuming? Yeah, these are differentiable, right? Near x equals to c. So in other words, I can calculate f prime of x and g prime of x. In this case, to the right of c is really what I'm interested in, right? So if f of x and g of x are differentiable, right? What does that imply? They're also continuous. So if, f of x, g of x, differentiable at x equals to c implies that they're what? Continuous at x equals to c, right? But if f of x and g of x both go to 0, that implies that f of c is equal to g of c, which is also equal to 0, right? Because a continuous function has to match the value of its limit at the limit point, right? by definition. All right. So assume that f prime of x over g prime of x goes to gamma as x goes to c from the right. Now I need to think for a second here. All right, so now we're going to use the Koshi mean value theorem. If you think about it, for each x, an element of, let's say, c comma c plus epsilon, he uses h in the book, but whatever. There exists some r in the open interval from c to c plus epsilon, such that what? For which, let me put by Koshi's mean value theorem applied to the closed interval c to x, f of x over g of x, right, is equal to what? Well, that's equal to f of x minus f of c over g of x minus g of c. Why is that? We just got done arguing that g of c and f of c were 0, right? So this is just an identity. But then what is Koshi's mean value theorem applied to the closed interval from c to x? What does it say? It says that there exists some r in here. Well, actually it's in here for x, but then that fits inside here. All right? Such that what? Such that that's equal to, f prime of r over g prime of r, right? So it follows, right, from this identity then, that if this goes to gamma, all right, if this goes to gamma as x approaches c from the right, then so does this, right? Does that make sense? If this doesn't make sense, let me show you a different argument of the same alternative presentation of this. If we look at the limit as x goes to, let's say, a of f of x over g of x, all right? That's the limit as x goes to a of f of x minus f of a over x minus a over g of x minus g of a over x minus a, provided what? So if f of a and g of a are 0, you'd have that's 0, right? And I just divided the top and the bottom by x minus a. But if you can break that up, right? You see, this is the way, the sort of plausibility argument most calculus books give. I didn't see it in his book. I don't know if it's in there or not. I don't have a photographed memory what I have read or haven't read in there, but I don't think I've seen this argument. And I think this argument is worth seeing because it might be more convincing than this longer, but probably more correct argument. if I have f and also g of x being differentiable at a, that means they're continuous at a, so f of a and g of a are 0, right? So I can take this quotient, replace it with this quotient, because I'm just dividing top and bottom by x minus a, right? Then you break it up into the quotient of the limits. This assumes, of course, that these exist. What is needed for these to exist? Well, certainly if f prime of a exists and if g prime of a exists, well, that would be what we have, right? Now, the scope of this is rather limited, right? This assumes that, in fact, the derivatives are both continuous, and that, of course, is not necessary. So this is not the greatest argument, but here's another reason that f prime of x over g prime of x should have the same limit as f of x over g of x in the case that the derivatives are also continuous. So in the case of continuously differentiable functions, we have an even kind of easier proof, which is this. Does this might make more sense to you guys, I don't know. Nothing makes sense to you guys? I tried. Now, let's just stop and smell the roses here. I mean, the conclusion of this is, so that implies then that the limit as x approaches c from the right of f of x over g of x is also equal to gamma. There's probably a few more sentences to write there to make it really careful. Now, here, that is what it is. I mean, this is an alternative special case proof again. But maybe we can get some intuition from this calculation. What this shows you is that if you're comparing two functions as x is approaching a, right? In some sense, the limit is really just boiling down to what? How fast the function f approaches a and how fast the function g approaches a. So L'Hopital's rule is saying something like, to analyze the limit of a quotient, we can compare how fast the top function is going to a versus how fast the bottom function is going to a. And the ratio of those speeds, let's say, is the same as the ratio of the functions themselves. And if you have matching speeds, right? If you get like 0 over 0 or infinity over infinity, then you can apply L'Hopital's rule again, and then you can compare accelerations, right? And if that doesn't work for you, if they're still comparable, if it's still indeterminate, then the problem's a jerk, because you have to compare third derivatives. Anyway, you see where this is going. But there you go. There's a proof of L'Hopital's rule, at least in this case. Now, the book also has a simple argument to derive the infinite case from this using the exchange. You have this identity. The limit as x goes to infinity of f of x is equal to what? The limit as t goes to 0 from the right of f of 1 over t. So you have this interplay between right limits at 0 and limits at infinity. And so you can use this identity and just basically apply it to L'Hopital's rule and get the L'Hopital's rule at infinity from the one at a finite point. And the argument I showed you for a right limit can be adapted for a left limit. But anyway, I think I have said enough about all that. I'm gonna stop here for a minute and ask if you have any questions about the material, but then I will go on. Yeah, pretty much, except that you'd be looking at something like c minus epsilon to c and so forth. But this is, again, I'm basically just sharing with you what's written on page 557 of the textbook. I haven't really added too much there. I mean, my main contribution was to introduce delta f and delta g, because if you look at his proof, he writes f of b minus f of a and g of b minus g of a like 5 times. I don't know. I got tired of writing it. That's why I invented the delta f and delta g. I think it's easier to see what's going on with the delta f and delta g notation, but you can disagree if you want. So with that, any questions about the homework? I have a couple minutes. I can talk about homework. Do you have any remaining questions about L'Hopital's? All right. What about it? Oh, this one. Yeah, they asked me about this yesterday in the other section. So basically there, what you need to know is the derivative. So I'll just remind you, the derivative with respect to time of the integral from, say, a to t of f of x dx is equal to f of t. Now, I guess there you've got d dx of the integral from, say, a to t. I forget what the notation is. One of these or the other is useful in that problem. So basically, just look at what you got. You got like 1 over x times the integral from, I guess it's 0 to x, right? Is this right? So if you look at this expression, this is really the integral that's type 0 over 0. You can apply L'Hopital's rule. And if you know fundamental theorem of calculus part 1, you can differentiate the top. That's pretty much all I should say. If you want to see me say more, you can watch the video from yesterday. I solve it in its stupid entirety there. But I feel guilty about doing that, so I'm not going to do it again. Other questions? Yeah. 36 on 11.6. All right. Limit as n goes to infinity of n to the k over 2 to the n. Did I write that right?
That's right.
And is it k? 2 to the, what's k?
It doesn't say, it's just k. I assumed it was just constant or something.
Oh, okay.
I mean, it doesn't specify, but that's what I thought it meant.
Yeah, no, that's fine. And why doesn't it matter? They must be asking us to do what? Show that this is true for any real k. Right? Now, it's easiest, I think, to interpret if k is a whole number. So let me set my sights a little bit lower. Let's assume that k is a natural number. Okay. I have a suspicion that this is true even if k is like pi. Right? Well, let's say this. If k is, well, first of all, if k is less than 0, right? If k is less than 0, this is what? It's just like, if k is less than 0, then n to the k is like 1 over n to some positive power, right? That goes to 0 as n goes to infinity. So does 2 to the n. So the answer is 0. If k is less than 0, the answer is clearly 0 just by algebra. So in order to make this interesting, I think I just need to say k is greater than 0. That'll do it. I think I can make sense of it, yeah. So apply L'Hopital's rule. Which type is this? This is infinity over infinity. And what did I just do if I apply L'Hopital's rule here? I need to make a parenthetical comment. I'm extending n continuously, right? I'm elevating n to be a real variable, not a sequential variable. If you don't like this, if you're like pure of mathematical heart and you feel the desire to write more, you are free to introduce f of x, such that f of x is equal to x to the k over 2 to the x. Observe that f of x is continuous on all reals, and consequently you can study L'Hopital's rule on the corresponding continuous function, derive the necessary result, and then go back to the sequence by plugging in x equals to n. We replace all of that by just saying extend n continuously. All right, so L'Hopital's rule, what does this give us? This gives us k times n to the k minus 1, right? Here we got what? Natural log of 2 times 2 to the n. Then what? If k minus 1 is less than 0, then the answer is 0, right? Because if k minus 1 is less than 0, then we again have something where the top is going to 0 and the bottom's going to infinity. So the whole thing goes to 0, right? Again, if this is negative, that means this is really like k over 2 to the n times n to some positive power, which goes to 0, right? Do you guys with me? Does that make sense? Otherwise, what? It's still infinity over infinity, right? So what do you do? Apply L'Hopital's rule again. That's right. What's that give us to? K times k minus 1, n to the k minus 2. Natural log of 2, natural log of 2, 2 to the n. And then you just keep doing this, right? Whatever k is, it can't, if k is like 32.7, right? After the 33rd application of L'Hopital's rule, you'll have a negative power upstairs, right? Because if you differentiate 33 times, you subtract 33 powers, 32.7 minus 33 minus 0.3. That 33rd application will bring the top power below 0, hence the numerator will go to 0, the bottom still goes to infinity, the net thing goes to 0. So you can see from basically repeated application of L'Hopital's rule, that equals to 0. Moral of this story is what? In a street fight between an exponential and a power function, always bet on the exponential. Okay. Sorry. Trying to make math more fun. Did it work?
A little bit.
A little bit, okay. I try. Yeah.
53.
If I brought prizes? What if I just randomly pulled out a Nerf gun and shot you guys? That would be fun, right? What's that? You'd be like, only if we can shoot back? I'm sorry, what?
53, I set it up, but I reached a point where I got a type infinity minus infinity. I wasn't sure to turn that into a L'Hopital rule.
50. Ooh. Here we study asymptotics. So f of x and g of x are said to be asymptotic as x approaches infinity if their difference is 0. And likewise at minus infinity. So you're supposed to show that the am I on the right problem?
Yes.
So it's 11.6.
Yeah.
Okay. So you're supposed to show that the hyperbolic arc, all right, is asymptotic to the line that's given. Now, let's see here. He's got what? I think his hyperbola that he's starting with, I really don't want to. Fine, I'm going to have to write it out again. Who am I kidding? Sorry, I'll try to stop being lazy. They do pay me to teach 2 sections of calculus. I should actually teach 2 sections. I think the hyperbola we're starting with, but they didn't even say, is what? X squared over a squared minus y squared over b squared equals to 1. This is a hyperbola, right? Let me just add a little backstory to this problem. So if you solve this for y, what do you get? Or is it the other way around? See, he's got x squared minus a squared square rooted. X squared. Yeah. So if I multiply this by a squared, I get x squared equals to, well, I get x squared minus a squared y squared over b squared equals to a squared, right? So this gives me x squared minus a squared is equal to a over b, quantity squared, y squared, all right? Assume a and b are positive, and you get y is equal to b over a square root of x squared minus a squared. Okay? Now, what does this thing look like? If x and y, well, like if y is much, much greater, essentially this looks, if you just ignore the 1, right? And you put these equal to 0, what do you got? You got like y is equal to, ignore the 1, and just put these equal, you get x, y is equal to, what is it? I mean, the asymptotes here are what? Remember the asymptotes for hyperbola? Oh, I could just look at this, right? So if you think about this, for x really, really big, what is this essentially? Right? So this is y equals to b over a times x. That's the asymptote of the hyperbola. Now, they have given you a careful definition of, let's see, where does this, is this in here or is it up here? How do you guys figure it out? How about put x equal to 0? X equal to 0 gives me minus y squared equals to b squared. A very hard equation to solve with real numbers. In other words, there is no point on the graph with x equal to 0. It follows that this is one of those sideways opening hyperbolas, like so, all right? And there's also a branch over here. That's a hyperbola. All right, finally getting to it. So the point of the problem is to show that this red curve is asymptotic to this green curve. So what you're supposed to show, right? The red curve has what equation? That one, right? The green one's that. Allegedly, these are asymptotic, which means the limit as x goes to infinity, we're supposed to be able to show that, and you pick it, whatever you want. I'm going to say b over a x minus b over a square root of x squared minus a squared. Oh, I mean, you could either look at the green minus the red or the red minus the green. Either way, I have to show the difference limits to 0 as x goes to infinity. That's what's the definition of f of x and g of x being asymptotic. As x goes to infinity, their difference must be 0. Does that make sense? I mean, it's a definition, so. Right, that, exactly. This is, at the moment, all I've done is just set up the problem. This is all the problem statement. Not all of this is written in the problem. I want to explain where the problem's coming from. I think we've done that. So, but this is a kind of limit we haven't dealt with yet. This is an infinity minus infinity. So I'm going to ignore it. Let's just ignore the, I'm not going to work this exactly, okay? But let me work a very similar problem. So how about this? The limit as x goes to infinity of x minus the square root of x squared minus 1. How would you do this? See, that's a pattern that I don't think we've faced in here just yet, but it's definitely one of the examples we should be able to solve. That's infinity minus infinity, right? Which is not 0, right? Well, I mean, it may or may not be. It's indeterminate, generally speaking. So what do we do? What's our usual trick for this kind of algebraic problem? Rationalization, basically, right? So we do. And usually, I mean, before you usually face something where you had a sum of radicals in the denominator, and then you multiplied by, like, the rationalization of it to bring the radical upstairs. In some sense, we need to kind of undo that because L'Hopital's rule only works for quotients. So we kind of have to make a mess of this expression in order to be able to work with it. And so it's a little bit sneaky, but this is the trick. I'm pretty sure it'll work. We'll find out soon. So what you do is just take the radical, make it plus, and multiply by basically 1 in this creative fashion. Now doing that will do what? That will make the radical cancel out upstairs. Because I get x plus the radical minus x times the radical. So the radicals cancel out upstairs, and we're just left with what? Did I say minus? Excuse me. There should be, that's a minus 1 inside the radical, guys. Don't be fooled. Otherwise, it doesn't do what I want it to. Okay? The plus is outside the radical. The minus is inside the radical. You got it? X squared minus 1. So I've got x squared minus 1, excuse me, squared, divided by x plus the square root of x squared minus 1, which is what? Right? As x goes to infinity, what do you got? 1 over infinity plus infinity, basically, right? Which is still huge. And so it's 0. So this shows that y equals to x and y equals to the square root of x squared minus 1 are asymptotic. So you just have to go through a similar calculation with the a floating about.
That's where I got stuck. I got the infinity minus infinity, and I wasn't sure to turn that into like an infinity over infinity or 0 over 0.
Right. Yeah. This is like a much less. I mean, we worked that number 15. Remember 1 over x squared, 1 over sine squared minus 1 over x squared. That was our token infinity over infinity example, I think, so far in here. But that one was much nastier. This is a nice infinity minus infinity example. Of course, it doesn't have to work out to 0. You can see that if this had turned out differently, you could have ended up canceling things. And like if this was constructed to, let's see here. If I go like x minus the square root of x squared, plus 2x or something like that, then what would happen? The same calculation, you'd end up with what? The x squared still cancel. You'd end up with a minus 2x upstairs. And so that would like go to 2. If you can play with this to make it come out to whatever you want by just like adjusting what's inside the radical. So, but is that, you think you can do it now?
Yeah.
Okay, cool. Other questions? Well, there'll be more time for more questions tomorrow. I'm going to go on to the next topic and the final topic before the test, which is that of improper integration. So what is a improper integral? So there's basically two kinds. Improper bounds or you have improper integrands. So improper bounds is kind of just what it sounds like. So for example, you can have something like the integral from 0 to infinity of e to the minus x dx. What would that mean is the question, all right? An improper integrand would be something like integral, say, from 0 to 1 of dx over the square root of x. See, the bounds there are fine. We know what 0 to 1 integrals mean, right? But 1 over the square root of x is not defined at 0. right? So what does that mean? It has to be defined in some kind of sneaky way. And then you have examples which involve both of these, all right? Like an example which has got both types of improperness would be something like integral, say from minus infinity to infinity of dx over x. That doesn't exist for about 4 different reasons. Okay, so we'd like to define these sorts of things, all right? And I could give you some kind of like grand overarching definitions for both of these, but I think it's better for me just to show you examples and to give you the principle of our definition, which is that whenever there's some sort of improperness, we define it in terms of the appropriate limiting process. All right? So let's start with my first thing. Integral from 0 to infinity of e to the minus x dx. How would that be defined? We have to define it in terms of things we already know. Okay? So here's how it goes. You take the limit as, let's say, b goes to infinity of the integral from 0 to b of e to the minus x dx. Does that make sense? Well, anyway, that's the definition, so if it doesn't make sense, that's unfortunate because that's the definition you're stuck with. But this, well, that's an ordinary integral, so we can do that, right? This is the limit as b goes to infinity of what? E to the, well, minus e to the minus x, right? Evaluated from 0 to b, which is what? Minus e to the minus b plus e to the 0, right? So as b goes to infinity, what's e to the minus b go to? What's that? 0, right. And this is 1, right? So the answer is 1. See? Not so bad, is it? Nothing to be scared of here, really. They don't have to be hard. And so what we're doing is we're calculating the area under the e to the minus x graph from 0 all the way out. It's the area under that curve. So you have an infinite length, but the height of it gets infinitely small in such a way that the area bounded is finite. In fact, it's 1. Neat, huh? I think it's neat. I don't know. You can disagree with me if you want. How about my next example? The integral from 0 to 1 of dx over the square root of x. How's that defined? What's the trouble here is in your face. I wrote infinity in the bound, right? That's clearly outside the box that we were before in, right? This, on the other hand, this one is deceiving. Because it looks kind of like it's an ordinary integral, right? But the devil's in the details here. So what we have to mean by this is the limit as, let's say, a approaches 0 from the right of the integral from a to 1 of dx over the square root of x. Does that make sense? If we have trouble at one of the endpoints, we approach it. Right? And that's how this has to be understood in terms of this limiting process. Now, of course, this we can say is what? Limit as a approaches 0 from the right. What's the integral of this 1 over the square root? How about twice the square root, right? 2 times the square root is the integral of 1 of the square root. If you differentiate my antiderivative, you'll get back to that, okay? And so what we're faced with here is the limit as a goes to 0 from the right of twice the square root of 1 minus twice the square root of a. as a goes to 0, what happens to the square root of a? Goes to 0, right? Yeah, so this example is harmless as well. The answer is 2. It's entirely possible that you could have done this without writing the limit, right? And you wouldn't have even known that what you did was implicitly an improper integral. You could gloss over this and still be correct, right?
If it was from -1 to 1, like in the very beginning, you said 0 to 1.
Mm-hmm.
And you just did would be a goes to...
This one?
Oh, not the one you just...
Or that one? That one's just like, yeah. Like I can't even start if that's the case, because like the square root of x is not defined. Like one point where it's not defined, either the interior or on the edges we can deal with. A whole string of points, a continuum of points where it's not defined, I have no way around. So you could square root of minus x square root of a negative number is imaginary. I mean, that properly belongs to a different course. Well, I picture the integration region, which would be like 0 to 1, right? And I think about if it's here that I'm omitting, right? That means I have to approach it like that from the inside. That's a right limit. Geometrically, what's going on here is what? What does the 1 over the square root function look like? It's one of these deals, right? And what we just figured out is that the area from 0 to 1, which is like this, and it goes up to infinity, that area is 1. It's not 1, it's 2. Right? I mean, you can see that this is 1, right? So apparently this area up here is 1 as well. Let's look at something a little bit sneakier. Integral, say, from -1 to 1 of dx over x. All right, so here's how not to do it. Natural log of the absolute value of x, evaluated from -1 to 1. Natural log of 1 minus the natural log of the absolute value of -1, right? Find absolute value of 1. Anyway, we get ln 1 minus ln 1. And forget about 1. Let's make this 2 to make it more interesting. Sorry, guys. So it's what? 0. This would be incorrect. This is, in fact, not correct. And the reason that is, let me put a big old one of these through that, just so you don't miss it. Why is this incorrect? Because what happens to x at equal to 0? Right, it's not. So the way these sorts of problems are dealt with is you have to break it up into pieces. Now, conceptually, there's a couple different ways you could have gone here. But here's the standard definition. We do like this plus this. So you break it into 2 improper integrals of the type that we already dealt with over here. Okay? And then what you've got is, on the one hand, the limit as b goes to 0 from the left of the integral from -2 to b dx over x, plus the limit as a goes to 0 from the right of the integral from a to 2 of dx over x.